This is part 3 of the series Calculus Prerequisites, and in this part we're continuing on with our idea of breaking apart polynomial functions, and we're going to look at synthetic division now. Synthetic division works when your divisor is a linear binomial. It only works in that instance, but in that instance it makes division with polynomials very, very straightforward. So let's take a look at this first one, and we're dividing x squared plus 3x plus 5 by x plus 1. Now, since we're using synthetic division, what we're using is coefficients. We're going to eliminate all the variables, and we're just going to use placeholders in the place of those variables. Now, since we're dividing by the factor x plus 1, we want to divide by the actual x value. So if x plus 1 equals 0, then x has to equal negative 1. So we're going to be dividing this polynomial by negative 1. So we'll put a negative 1 out front. And traditionally, the way we write the division symbol, it's an upside down division symbol, which kind of messes with people's heads from time to time. And then we're going to write inside here, we're writing the coefficients of our dividend. So the coefficient of the squared term is 1. And just as in polynomial long division, we have to have a term in progression. So there has to be, if there's a squared term, there must be a linear term and a constant. If we had a quartic, we would need a cubic, quadratic, linear, and constant. And if there's no values given, you would just put zeros in placeholders here. In this case, we have one for everything. So this is the squared term. The linear term has a coefficient of 3, and the constant is 5. Now, the first thing you do, some people like to do this, they like to write an arrow indicating that this term always goes down here, because there's really no operation that goes on. Now what you do is you multiply this divisor number by this value, and you put the result under the next value. So this times this is negative 1. And now we add going down. So 3 minus 1 is 2. Then we multiply this by this and put the result here. Negative 1 times 2 is negative 2. And then we add going down, plus 3. So here our result is going to be, since we took a squared term and divided it by a linear term, you know that x squared divided by x is a linear term. So this is a linear coefficient. So this is going to be 1x, or just x. This is the constant 2, and this is our remainder, plus 3 over our divisor, x plus 1. So this is equivalent to this expression here. And just like we did before, we can verify that just as a cross-check. Let's multiply through and get a fraction with a common denominator here. I'm just going to reproduce the x over here. And this is x times 2, which is plus 2x. And 1 times 2, which is plus 2, plus 3. What I'm doing here, in case you don't know what this is, I'm basically making believe that there's a 2 over 1 here, and I'm taking these two fractional terms and combining them to generate one expression with a common denominator. So you multiply this by this by this with this sign, and this by this. And that gives us our result. So this times this was that. This times this was that. This times this is this. And this piece here divided by this times this is x plus 1. Now we do the same thing using x over 1. So this times this gives us x squared. This times this plus x. This times this plus 2x plus 2 plus 3 all over this times this, which is x plus 1. And to simplify that, we have x squared. X plus 2x is plus 3x, and 2 plus 3 is plus 5 over x plus 1. And you can see that reproduces our original expression. So this is in fact equivalent to this, and that's the goal. You're going to see in calculus it's going to be more difficult to work with this, doing some of the operations we have to do, but this is very easy and very straightforward. So this is an alternate form that we're putting this into to make it simpler to work with, and that's the whole point of this. And this brings us to a very, very common statement that I make all the time. Calculus is easy. It's the algebra that's hard. Most of the work you're going to do in a calculus class is algebraic manipulation and changing your result from your calculus result to some simplified form. The calculus part is the easy part, and simplification and reordering terms, that's the more difficult part most of the time. All right, let's move on to the next problem. Here, our divisor is x plus 3, so our divisor value x equals negative 3. We put in our bracket. Now here we have a quartic term, so that coefficient is 1, but we're missing a cubic term, so it's 0. Then we have a squared term here, which is negative 10, a negative 2 for a linear, and a 4 for a constant. Now again, we pull down the 1. You don't have to write the arrow if you don't want, but you could if you wished. 3 times 1, negative 3, and add. Multiply gives us 9. Add. Multiply. We get 3. Add. Multiply. And add. So we have, this is a cubic, because a quartic divided by a linear is going to be a cubic. So this is x to the third. This is squared, minus 3x squared. This is linear, and this is constant, 1 over x plus 3. Now, it's always a good idea to check your results just to make sure that the rest of your work isn't off, because there's nothing worse than working through a calculus problem, making a mistake at the very first part of the process, and if this is incorrect, everything beyond this is going to be incorrect, of course. So if time permits, it's always a good idea to check this. I've already checked this. This is the correct value. I'll leave it as an exercise for you to verify that this is equivalent to that. So let's move on to another set of tools that you looked at, and those are the remainder and factor theorems. The remainder theorem states, if a polynomial f of x is divided by some factor x minus k, then the remainder is f of k. In other words, if you take some polynomial function f and you divide it by some value, then evaluating the function at that k value will give you the number of the remainder. Let's look at an example just so that we understand what's going on here. So let's say that x squared plus 2x minus 3 is our f of x, and our x minus k is x minus 2. That means k has to be 2, because if this is x minus k, k has to be 2. Now, what we're saying then is that the remainder of this division, the division of this by this, is going to be the same as you get if you evaluated the function at the value of 2. So let's go ahead and do that and see what that value is. So evaluating this expression at 2 means this is, for every place we see an x, we're going to write a 2. So that's 2 squared plus 2 times 2 minus 3, which gives us 4 plus 4 minus 3, which is 8 minus 3, which gives us 5. So the idea behind this theorem is that this value should result in a remainder of 5. Well, let's use some synthetic division just to do this really quick. And we're taking our factor of x minus 2 that gives us a k value of positive 2. And our quadratic coefficient is 1, linear is 2, constant is negative 3. Multiply, add, multiply, add, and we can see that yes, in fact, our remainder is 5. So we get x plus 4 plus 5 over x minus 2. So the remainder is 5. And this is what they're talking about with the remainder theorem. So it's a quick way for you to determine if in fact some factor gives you a particular remainder, what the final remainder is, whether this factor is going to divide evenly into that dividend. Now the factor theorem is very closely tied with this, and what the factor theorem says, a polynomial f of x has a factor x minus k if and only if f of k equals 0. In other words, if there's no remainder by dividing f by this, then this value is a factor. So let's take a look at this same expression, x squared plus 2x minus 3, and divided by x minus 1. So we want to determine if x minus 1 is a factor of x squared plus 2x minus 3. So the way we do that is to say f of k, k being 1 here, if we evaluate this at the value of 1, the x value of 1, and this comes out to be 0, then this is in fact a factor. So evaluating this at 1, 1 squared plus 2 times 1 minus 3 gives us 1 plus 2 minus 3. That's 1 plus 2 is 3, minus 3 is 0. So yes, in fact, x minus 1 is a factor of this expression, and we can see that very quickly again. If we have 1, 2, negative 3, and we multiply, add, multiply, and we get a 0 remainder. So x plus 3 is the other factor. So we know that x plus 3 and x minus 1 are factors of this. Remember, up to this point, most of what we've been dealing with has been factorization, and this is just another tool that you learned in the past to help you through with that. So this is the remainder and factor theorems. In the next video, we're going to take this one step further, and we're going to look at the rational zeros test, and that's going to be applied to higher order polynomials beyond squared type polynomials. So I will talk to you in the next video.